Walk into a quiet forest and it feels like almost nothing is happening. The leaves barely move, the stems stand still, and the green world seems completely silent. But that silence is not the truth of the forest. It is only the truth of your body. If you could attach a sensitive vibration sensor to a single plant stem, the forest would change instantly. The quiet stem would become a trembling tower of signals, calls, warnings, and hidden conversations. Tiny insects called treehoppers send messages by shaking the plant tissue beneath their feet. They do not sing into the air the way birds do. They sing through the surface they are standing on. To us, the plant is silent, but to them, it is a living telephone wire. A stem can carry courtship calls, danger signals, rival challenges, and the tiny footsteps of enemies. The strangest part is not that treehoppers do this. The strangest part is that they are only one small piece of a much larger hidden world. Across insects and other animals, life is constantly sending information through surfaces, fluids, and air. The world is filled with messages that never become sound to human ears. They pass under our shoes, through water, across leaves, and along strands of silk. We were taught that touch begins when skin meets surface. A hand touches a table, a foot touches the ground, a finger touches glass. But that is only the most obvious version of touch. In nature, touch does not always require direct contact. Every moving body pushes against something. A fish pushes water, a spider shakes silk, an elephant compresses earth, a wing disturbs air. Those pushes travel outward as pressure, ripples, currents, vibrations, and waves. For animals built to detect them, those waves are not background noise. They are information. Touch can become a sense that reaches far beyond the body. And to understand that, we first need to meet animals that turn direct contact into a superpower. Deep underground, the star-nosed mole races through tunnels where vision is almost useless. Its face carries 22 soft, fleshy rays arranged like a living star. That star looks like a strange nose, but it behaves more like a pair of hands. As the mole moves, it presses the star against the tunnel walls again and again. Each touch gives the brain a fast burst of information about shape, texture, and space. The mole does not slowly inspect the darkness. It rapidly samples the world, building a map from touch while sprinting through soil. When it strikes a tiny worm or grub, the decision happens almost instantly. Identify, grab, swallow. The whole hunt can be faster than a human blink. For this animal, the face is not just a face. It is a high-speed scanner built for a world without light. A sea otter uses touch in a very different world. Floating in cold coastal water, it searches with paws that look almost clumsy, but those soft paws can make incredibly fast decisions from tiny differences in texture. In darkness or cloudy water, an otter can sort food from useless stone by feel. To a human hand, two objects may seem nearly identical. To the otter, one is dinner and the other is just weight. This is direct touch at its finest. But some animals use contact for something far more disturbing. The emerald jewel wasp hunts cockroaches, not simply to kill them, but to control them. It needs the cockroach alive, calm, and usable as food for its young. To do that, the wasp drives its stinger toward the cockroach's nervous system. The stinger is not just a weapon. It is also a sensory tool, covered with receptors that help guide the attack. Inside the victim, the wasp feels for the right target before delivering its venom. The venom does not turn the cockroach into a movie zombie, but it can strongly alter the animal's behavior and make it strangely easy to lead away. The wasp has turned touch into a surgical method of control. These animals show how powerful contact can become when evolution sharpens it. But the real twist begins when touch leaves the body entirely. On wet beaches, shorebirds called red knots search for buried clams hidden beneath the sand. Their prey is out of sight, locked under wet grains where eyes cannot help. The bird does not simply stab randomly and hope for luck. When its bill enters the wet sand, it creates tiny pressure changes in the water between grains. If a buried shell interrupts that pressure field, the pattern changes. Sensitive structures in the bill can detect those changes and reveal where the hidden object is. It is not exactly seeing through the ground. It is feeling the shape of something it never directly touches. This is the first step into remote touch. The body sends a disturbance into the world, then reads how the world answers back. In water, this ability becomes even more powerful. An alligator can wait in muddy shallows, motionless enough to look like part of the swamp. Its armored skin makes it seem like a blunt, insensitive predator, but the edges of its jaws are covered with tiny pressure-sensitive domes. Those domes can detect delicate disturbances moving across the water. A small splash, a drifting ripple, or an animal drinking at the shore can become a signal. The alligator does not need clear vision to know that something has touched the surface. It can feel the water changing around its face. Fish live inside this pressure world all the time. Every swimming fish pushes water ahead of its body and pulls water behind it. That movement creates a flowing field that bends around rocks, plants, prey, and predators. Along the sides of many fish runs a sensory system called the lateral line. It detects changes in water movement that the fish's eyes may never notice. A blind fish can still avoid obstacles because the water itself is reporting their presence. A school of fish can turn together because each body feels the movements of nearby bodies. What looks like perfect visual choreography is partly a shared sense of flow. The water becomes a moving map. But water can do something even stranger. It can remember motion after the animal is gone. When a fish swims through the sea, it leaves behind swirling trails of disturbed water. These wakes can persist long after the fish has disappeared from sight. A harbor seal can use its whiskers to detect those ghostly trails. The seal sweeps its whiskers through the water and reads the leftover pattern of movement. The prey may no longer be there, but its path still exists as a fading physical trace. To the seal, water is not empty space. It is a record of what recently passed through it. This creates a problem that should ruin the whole ability. A swimming seal creates its own turbulence, and that noise should bury the fish's delicate wake. But seal whiskers have a special wavy shape that reduces vibrations from the seal's own movement. Instead of blinding itself with its own motion, the seal quiets part of its sensory noise. It can hunt by reading the recent history of water. Manatees take the idea even further. Their large bodies are covered with sparse, sensitive hairs. These hairs are not there for warmth like fur on a land mammal. They help the animal detect movement and vibration in the surrounding water. A manatee does not need sharp vision to understand the space around it. Its whole body becomes a broad, slow, living touch organ. The ocean presses against it, and the animal listens through its skin. Remote touch does not stop at water. It rises into the air. A mouse sweeping its whiskers in the dark is not passively waiting for contact. It is actively sampling the space in front of its face. Long whiskers brush walls, gaps, food, and obstacles before the animal commits its body. Shorter, more sensitive whiskers can then inspect the details. The mouse is not just moving through darkness, it is painting the darkness with touch. Some spiders are sensitive to air movement at a level that seems almost impossible. On their legs, fine hairs can respond to extremely small disturbances in the air. When an insect flies nearby, it pushes a faint wave of air ahead of itself. The spider may feel that tiny disturbance before the prey ever makes contact. In the dark, the air becomes a warning system. A fly thinks it is approaching silently, but its own wings are announcing it. Crickets use similar air-sensitive hairs to detect danger from behind. A hunting spider may creep quietly, but its body still disturbs the air. To a cricket, that disturbance can be the difference between escape and death. Even peacocks add a tactile layer to what looks like a purely visual display. A male shakes his huge tail feathers during courtship, creating subtle air vibrations. The female does not only judge color and shape, her crest feathers can respond to the rhythm of his display. Part of the dance is seen, but part of it may also be felt. Bats also depend on touch moving through air. Fine hairs on their wings respond to airflow during flight. Those signals can help a bat sense when the air over its wing is changing. In fast turns and sudden maneuvers, that feedback matters. The bat is not just flying through air. It is feeling the air sculpt itself around its wings. But the most ancient and powerful tactile channel is not above us. It is under our feet. We think of the ground as solid, dead, and silent. For many animals, the ground is closer to a giant communication network. Every footstep, stomp, scrape, landing, and struggle sends vibration into the surface. The earth carries those signals farther than we usually imagine. In the savanna, elephants can respond to low-frequency vibrations traveling through the ground. Their heavy feet are not just tools for walking. They can help detect tremors moving through soil and rock. A distant group may stomp, run, or call, and part of that disturbance enters the ground. Another elephant, far away, may feel information arriving through its feet. To us, the dust is quiet. To them, the ground may carry warnings, movement, and the presence of other giants. On a much smaller scale, a sand scorpion turns loose desert grains into a targeting system. It waits at night with its legs spread across the sand. Small slits in its body can detect vibrations arriving through the surface. When an insect lands nearby, the impact sends tiny waves outward. Those waves do not reach every leg at the exact same moment. The scorpion uses those time differences to locate where the disturbance began. In darkness, without needing eyes, the sand gives away the prey's position. The desert floor becomes a radar screen made of grains. Other animals use the same hidden channel for navigation. The golden mole lives beneath desert sand where ordinary hearing is limited. Its enlarged middle ear bones help it detect low-frequency vibrations moving through the ground. Instead of listening to the air, it presses into the sand and reads the world below. Vibrations from plants, wind, or movement can become landmarks in a place that looks empty. To a human, the desert may seem blank. To the mole, it is textured with physical signals. Humans have accidentally learned to hack this buried language. In parts of the American South, people use a technique often called worm grunting. They drive a wooden stake into the soil and rub it to create vibrations. Earthworms may respond by coming to the surface, likely mistaking the signal for danger. The trick works because the ground is not just ground. It is a medium that can be manipulated. A fake tremor can become a false alarm. This hidden sense can shape life before an animal is even born. In tropical forests, red-eyed tree frogs lay eggs on leaves hanging over water. The embryos develop inside soft, jelly-like clutches above the pond. Waiting too long can be dangerous, because snakes may attack the eggs. But hatching too early is also risky, because the tadpoles are not fully ready. So the embryos face a brutal decision before they have ever seen the world. They must decide whether a shaking leaf means rain, wind, or a predator's mouth. Research suggests they can respond differently to different vibration patterns. Random storm movement is not the same as the rhythm of a snake attacking the clutch. When the danger signal is right, embryos can hatch early and drop into the water below. They escape by reading vibration before they have lived a single day outside the egg. Touch is not only a sense for bodies that walk, swim, or fly, it can be a survival system for life still sealed inside a membrane. And then there is the spider's web. A web looks like a trap, but to the spider, it is much more than that. The spider at the center does not experience the room the way we do. Its vision is limited, but the silk is alive with information. A fly, a falling leaf, and a gust of wind do not shake the web in the same way. Each creates a different pattern of tension and vibration across the threads. The spider feels those patterns through its legs. The web becomes an expanded sensory surface, stretched far beyond the spider's body. In a sense, the spider is touching the room through silk. If prey stops moving, some spiders can pluck threads and read the returning vibrations. The web does not only catch insects. It tells the spider what has been caught, where it is, and how it is moving. But the most fascinating part is that the spider can change the instrument itself. By tightening or loosening silk, it can alter how vibrations travel across the web. A tighter thread may carry weaker signals differently than a looser one. The spider is not trapped inside one fixed version of reality. It can adjust the structure that feeds information into its nervous system. A hungry spider may become more responsive to smaller prey because the web changes what reaches it. The decision is not only happening inside the spider's head. Part of the decision is shaped by the silk, the tension, and the physical design of the trap. The spider's environment is not separate from its senses. It is part of the sensing system. That idea opens the door to something even stranger. If a web is a sensory network, then another animal can hack it. Tiny thief spiders can enter the webs of larger spiders and steal captured prey. They move carefully, timing their steps to avoid creating signals that expose them. Some predators and parasites can even manipulate web vibrations to deceive the owner. A thread can become a lure, a disguise, or a weapon. The spider thinks it is reading the truth of its world, but another creature may be writing false information into that world. This is the deeper story hidden behind the sense of touch. It is not just skin meeting surface. It is bodies disturbing the world, and other bodies reading those disturbances. A fish writes its path into water. A spider stretches its nerves into silk. A scorpion turns sand into geometry. A frog embryo feels death arriving through a leaf. An elephant may receive warning through the ground beneath its feet. Life is constantly pushing, shaking, bending, and rippling the matter around it. Most of those signals pass through us unnoticed. We cover our feet with rubber, separate ourselves from soil, and treat silence as emptiness. But silence does not mean nothing is happening. It often means the message was never meant for our senses. The world is not an empty stage where animals simply move around. It is a dense physical web of pressure, vibration, current, and contact. Every step sends a signal. Every wing beat leaves a disturbance. Every struggling insect, falling leaf, drinking animal, and moving fish changes the medium around it. Somewhere nearby, another living thing may be feeling that change. You are always touching the world. The unsettling truth is that the world has always been touching back.